In December 2025, Nvidia did something unthinkable. They wrote a check for $20 billion, not to buy a company, but to license a technology that was threatening to tear down their entire empire. For years, the GPU has been the undisputed king of AI. But in 2026, the physics of artificial intelligence fundamentally broke. We are witnessing a monumental paradigm shift from the static, compute-heavy world of AI training to the high-speed, unpredictable era of agentic AI inference. And the brutal truth, traditional GPUs simply cannot handle it. Stick around, because today we are decoding the physics of the inference bottleneck, the radical invention of the language processing unit, and how Nvidia's massive $20 billion gamble just reinvented the internet's core infrastructure. Historically, AI data centers were designed for one thing: training. That meant general-purpose graphics processing units engineered for massive, parallel throughput. But the AI of 2026 doesn't just answer static prompts anymore. We have entered the era of agentic AI, autonomous software and robotics constantly reasoning, using tools and running recursive loops in the background. This transition exposed a fatal flaw in the physical architecture of the GPU. To understand why Nvidia panicked, you have to understand the physics of the bottleneck. When you prompt a large language model, the execution splits into two distinct phases. First is the prefill phase. The GPU digests your entire prompt at once. This is highly parallel, and GPUs love this. But then comes the decode phase, the actual generation of the text. Modern transformers generate text autoregressively. That means it is strictly serial. The model cannot calculate the probability for token number 2 until token number 1 is fully generated and appended to the context window. For a single user stream, this runs at a batch size of exactly 1. Suddenly, the GPU's massive array of compute cores goes completely idle. The system is no longer constrained by processing power. It is entirely choked by its high bandwidth memory, or HBM. To generate just one output token, the hardware has to physically stream the entirety of the model's weights along with the active key value cache from off-chip memory, across a bus, and into the compute cores. Let's look at the sheer scale of this physics problem. A 70 billion parameter model, quantized to 16-bit precision, requires moving roughly 140 gigabytes of weight data, even on an advanced Nvidia A100 GPU with 2 terabytes per second of bandwidth. Reading those weights takes a minimum of 70 milliseconds per forward pass. That is an analytic floor, a hard physical speed limit. It doesn't matter how many theoretical petaflops of compute the GPU possesses. If the memory bus is saturated, the chip is bottlenecked. Physical testing proves this. While lower-tier L4 GPUs operate at roughly 81% of this memory floor, the mighty H100 only reaches about 27% utilization during short context decoding. Raw bandwidth increases simply do not yield proportional latency gains. And it gets worse. GPUs were designed for graphics and general workloads, meaning they use runtime dynamic scheduling. To generate a token, data has to traverse up to 6 separate tiers of memory, originating on an NVMe storage drive, moving to CPU RAM, crossing the PCIe bus into the GPU's HBM, stepping down into the L2 cache, which costs 258 to 743 clock cycles of latency on an H100, and finally reaching the L1 cache for zero latency execution. Because this relies on hardware-level arbitration, cache coherency protocols, and speculative execution branches, any routing delay cascades through the system. In the industry, they call this non-deterministic nightmare, jitter. Unpredictable latency spikes that ruin real-time AI. For voice bots and agentic workflows, jitter is a death sentence. Enter Groq. Founded in 2016 by the engineering architects responsible for Google's original tensor processing unit, Groq threw the GPU rulebook in the trash. They engineered a single-purpose inference accelerator optimized exclusively for sequential token generation. They called it the Language Processing Unit, the LPU. And their foundational breakthrough was violently simple: eliminate the off-chip high-bandwidth memory entirely. Instead of external HBM stacks, the LPU uses a massive distributed pool of SRAM, static random access memory, integrated directly onto the processor die. SRAM is the ultra-fast, highly volatile memory usually reserved for tiny CPU caches. It's incredibly expensive, power-hungry per bit, and low density compared to external DRAM. But it offers sub-nanosecond latency, By building a flat SRAM mesh, the LPU keeps all model weights and KV caches directly adjacent to the compute units at all times. The performance difference? It's not an evolution. It's an annihilation. An Nvidia H100 delivers 3.35 terabytes per second of memory bandwidth. A Blackwell B200 hits 8.0 terabytes. A single Groq 3 LPU? It integrates 500 megabytes of SRAM to deliver an unprecedented 150 terabytes per second of memory bandwidth per chip. Loading a 70 gigabyte model partition takes 21 milliseconds on an H100 and 8.75 milliseconds on a B200. On the Groq LPU's SRAM, a blistering 0.47 milliseconds. If SRAM integration is the physical engine of the LPU, the software-defined compiler is its neurological system. Groq's core engineering philosophy is simple. Determinism is speed. The LPU operates entirely without dynamic hardware schedulers. There are no caches to miss, no speculative execution branches, no reorder buffers to manage. Instead, the MLIR-based Groq Flow compiler ingests the entire computational graph of the language model and pre-computes the execution schedule down to the absolute clock cycle before the model ever runs. Inside the chip, the internal processing core, the tensor streaming processor, is inverted compared to standard processors. Functional units are arranged in distinct vertical columns across the silicon die. There are vector execute slices with over 5,000 ALUs and massive matrix multiply slices featuring a 320 by 320 array executing over 400,000 multiply accumulate operations per cycle. Operating as a programmable assembly line, 64 independent data streams constantly move data horizontally across the chip at 20 to bytes per second. The compiler perfectly orchestrates this barrier-free conveyor belt. To maximize this throughput without lobotomizing the model's reasoning capabilities, the compiler employs Groq's proprietary true-point numerics. Instead of blindly crushing a model down to an error-prone INT8 precision like legacy accelerators, TruePoint dynamically manages mixed precision formats based on layer-specific error sensitivity. It strategically applies 32-bit floating point to sensitive attention logits, block floating point to robust mixture of experts weights, and 8-bit storage for standard activations. Because the hardware features a massive 100-bit intermediate accumulator, it guarantees mathematically lossless calculations regardless of the input bit width. This delivers a 2 to 4 times throughput speedup without any measurable degradation on rigorous benchmarks like MMLU or human eval. But there's an obvious physical limitation. 500 megabytes of SRAM per chip isn't enough to house a massive 70 billion parameter production model. To overcome this, the LPU infrastructure must scale outward using tensor parallelism. In a traditional GPU cluster, scaling out across NVLink or InfiniBand introduces severe latency penalties. Routing data through network interface cards and intermediate layer switches creates the exact jitter the LPU was built to destroy. Groq circumvented this completely with a proprietary chip-to-chip interconnect known as RealScale. Operating on a plesiosynchronous protocol, the hardware utilizes hardware-aligned counters to mathematically measure and cancel out the natural crystal-based clock drift between chips. Because the hardware actively rectifies this timing drift, the software compiler knows the exact clock cycle a packet of data will depart one chip and guarantees the neighboring chip is ready to receive it. They linked the LPUs using a direct mesh dragonfly topology. No intermediate switches, no packet contention. A single Groq 3 LPU possesses 96 direct links operating at 112 gigabits per second, yielding 2.5 terabytes per second of aggregate bidirectional bandwidth per chip. At rack scale, a multi-node system can communicate with a microscopic end-to-end latency of just 1.8 microseconds. A fully deployed 256-chip LPX rack behaves logically as a single, massive computational core, yielding 128 gigabytes of on-chip SRAM, 40 petabytes per second of aggregate bandwidth, and 640 terabytes per second of scale-up communication. This extreme scale-out efficiency is what makes the transition to agentic AI possible. Agentic systems consume up to 15 times more tokens than traditional chatbots because they operate continuously, constantly evaluating and adjusting their state. Hyperscale cloud providers usually maximize their GPU cost efficiency through continuous batching algorithms. But grouping hundreds of independent user requests together inherently inflates the time to first token. In a real-time voice agent, a 1-second queue delay caused by GPU batching is catastrophic. Groq's deterministic latency guarantees sub-100 millisecond responses. Running Meta's Llama 370B model, a heavily optimized H100 cluster might push 30 to 100 tokens per second. Under identical conditions, the Groq LPU consistently sustains 280 to nearly 400 tokens per second. Smaller 8 billion parameter models achieve over 1,300 tokens per second. And this SRAM advantage is massively amplified by modern inference algorithms like speculative decoding. By using a tiny draft model to guess 10 tokens, and a massive target model to instantly verify them in a single parallel pass, the LPU's 1.8 microsecond chip-to-chip interconnect turns theoretical speedups into a highly stable, production-grade acceleration multiplier. The raw performance of the architecture ultimately translated into devastating unit economics. Under a tokens-as-a-service model via Groq Cloud, Groq was aggressively undercutting traditional GPU providers. For example, running a dedicated Nvidia H100 instance on Together AI costs roughly $4,653 per month. The identical model routed through Groq's serverless API costs just 79 cents per million output tokens. The mathematical break-even point occurs at an astronomical 5.9 billion output tokens per month. Below that enterprise-scale volume, Groq was significantly cheaper, infinitely faster, and consumed a staggering 10 times less energy per generated token. Groq was an existential threat to Nvidia's dominant high-margin data center business. So in December 2025, Nvidia executed a masterstroke. To circumvent immediate antitrust blockades from the FTC and European Union, they did not acquire the company outright. Instead, Nvidia paid a massive $20 billion premium, a 2.9 times multiple over Groq's recent $6.9 billion valuation, just to license the LPU intellectual property and heavily acquire their core brain trust, including founder Jonathan Ross and President Sunny Madra. Groq Inc. remained legally independent under a new CEO, but Nvidia had absorbed the software-defined SRAM crown jewels. This move immediately neutralized Nvidia's most formidable inference challenger and fast-tracked the ultimate hybrid AI data center, the Nvidia Vera Rubin platform. The industry is no longer homogeneous. Welcome to workload disaggregation and the 25% rule. Nvidia's new architecture mandates a 3-to-1 ratio of GPUs to LPUs for mixed inference fleets. The heavy lifting, ingesting million-token context windows and pre-filling the cache, is highly parallelizable and compute-dense. This task is routed exclusively to the Vera Rubin GPUs, utilizing their massive HBM4 memory capacity and 50 petaflops transformer engines. But the moment the prefill is complete and the KV cache is established, the workload transitions. The token-by-token generation phase, dominated by latency-sensitive routing, is seamlessly offloaded to the Groq 3 LPX coprocessor rack. By co-designing the hardware to divide the labor between the parallel compute of the GPU and the deterministic SRAM of the LPU, the Vera Rubin platform delivers up to 35 times higher inference throughput per megawatt for trillion-parameter models. For data center operators, that fundamentally resets the baseline economics, unlocking 10 times more revenue opportunity. The $20 billion check wasn't just a defensive maneuver, it was the admission of a new physical reality. The era of the general-purpose GPU trying to brute force every aspect of artificial intelligence is officially over. Through extreme co-design and strategic IP acquisition, the future of AI infrastructure is no longer a contest between parallel compute and deterministic latency. It is the highly orchestrated, heterogeneous integration of both. If you found this deep dive into the physics of AI hardware valuable, hit that subscribe button and leave a like. Want to understand how the foundational models running on this hardware are getting smarter? Click the video on your screen right now to explore the breakthroughs in agentic reasoning. I'll see you there.